why do we need that the range, suitable range of the temperature? Where is the okay? So depending on our enzyme. Okay, so let me check on this. The title here is already yeah, thermostable lipase from Geobacillus zalehi. Because of this, we have selected the range of the temperature for a thermostable enzyme. Why not we go to 100? We can, but normally over 80, we consider those enzymes as extremophile. Okay, extreme. Extremo. It's hard to type using this. Okay, so we just have this range so that we know what is the range of the temperature we should use. Okay, so we have also other papers. For example, 5+1 6. Let me try this. Yeah, co-adapted lipase. Okay. Let me try this. Okay, so for this lipase, outside our protease here, it is from Antarctic organism. Okay, it is from Antarctic Sea. And then it was known to have an activity at cold environment. That's why the preliminary screening was conducted at 40 degree. Okay, so after that, the purification was conducted, blah blah blah. Then okay, the temperature profile shows that the optimal temperature basically 40, not 4 degree. It was at 40, 20 degree. Okay, yeah. So we can see that why not they essay at 80? Yeah, that's really bad selection because we are aiming to find a cold enzyme. So, and then we know the microbe also isolated from saccharophilic organism. That's why we aim for the lower temperature. The range should be maybe 4 degree to 20 degree. Okay, so but not to forget here, there's some report saying that a saccharophilic organism meaning that a microorganism which can live in the cold environment, there's some study report that this organism having thermostable enzyme. So that's the powerful of the enzyme. A saccharophilic organism having 55 degree optimal temperature of the enzyme. There's also some report saying this one. That's why the research is always interesting because why you have a cold, you are coming from cold environment, why should you carry an enzyme which optimal at higher temperature? So that's why we need to ask the microbe. Okay, that's why we need to search for the answer. Okay, so now we go for the next one for the thermostability. Okay, so we do not have the thermostability here, but we discuss about thermostability. Okay, where's the Where it is now? Okay. So the thermostability here is referring to the at that particular temperature, how long the enzyme can survive. Okay, we have just now, we have here optimal temperature. Now we want to know the thermostability or temperature stability. Okay, so thermostability or temperature stability is a study where we can understand at which temperature and then for how long that particular enzyme will survive. I mean, the residual activity, what is left after a certain time of incubation. Okay, I repeat, thermostability or temperature stability is a study where we want to investigate how long that particular enzyme can survive in that particular temperature. Okay, for example, here, what is it? Okay, so for this case, what we have, I think I need, okay, I need to check. Okay, you can write down any question while I'm explaining this. Okay, so this is what happened. The A is for optimal temperature. The C graph is for the thermostability. Okay, so now we want to check. Okay, since we know that this enzyme is a thermostable enzyme, we're going to check the enzyme property or the enzyme, how long it can survive in that respective temperature. So for this case, we have selected three temperatures: 60, 65, and 70. So yeah, we do not blindly choose 90 or 100. We can. But the thing is, we need, if you incubate at 100, we know that this enzyme may be just gone, nothing left. Okay, so for this case, for this study, basically it is not one time we did. We need to do it multiple times so that we know what is the range for this. Okay, let me just interpret the first study here. Okay, we have selected three temperatures. Okay, we have selected three temperatures: 60, 70, 65, and 70. Okay, what happened now? You have this beaker, okay, containing your enzyme. Okay, yeah, similar setup. This, you have your enzyme here, put it here. Don't forget, we need to make it in milligram. For example, you incubated 2 milligram of enzyme. Okay, after that, this will be incubated at 60 degree. Okay, then we have second setup. Second beaker. You have here still 2 milligram of enzyme and then incubate at 65 degree. Okay, and last beaker, you will have, okay, 2 milligram of enzyme, incubate at 70 degree. Okay. Okay, so for even for invertase, you can do, maybe you want to do at 40 and 55, you can do it. Okay, or even at 25, you can do it if you want to select three temperatures. Okay, so for this thermostable lipase study, we have selected three different temperatures: 60, 65, and 70. We have used similar enzyme amount. Okay, 2 milligram, 2 milligram. Okay, so what happened here? Once you have added with this, okay, we let this okay, enzyme to be incubated for 30 minutes first. Okay, we let the enzyme to be incubated at the respective temperature for 30 minutes first. Okay, so what's next after 30 minutes? After 30 minutes, you need to take out maybe 0.5 ml of the enzyme. Okay, this one take out 0.5 ml of the enzyme. This one take out 0.5 ml of the enzyme. Okay, so this enzyme you take out, and then what's next? You do the assay at the substrate. Okay, we add the substrate, and then we do the respective temperature. For this study, we need to assay at 65 degrees because 65 is the optimal temperature for this enzyme. Okay, assay at 65 degrees. So we assay at the optimal temperature. Optimal temperature. Okay. So now, even though it was incubated at 60 degrees, okay, we take out 0.5, assay at 65 degrees. This one, assay at 65 degrees. Even this one, it was incubated at 70, assay at 65 degrees. Because 65 degrees is the optimal temperature. Okay, so what's next? Okay, once you have taken 0.5 ml or whatever ml you want to take, okay, after another 30 minutes, so that means after 60 minutes of incubation, okay, we take out another 0.5 ml. And then we assay at the substrate, Okay, so for this one, take another 0.5, and then this one take another 0.5. And then we proceed with the assay at this temperature, optimal temperature. So we need to do the same thing for 90 degree, 120 degree, 150 degree. So the enzyme basically has been incubated for 3 hours. No. 150 degrees is not 3 hours. It's 2 hours and 30 minutes, right? 2.5 hours, this one. This one will be 2 hours. So we have checked, we have performed the assay, we have checked on the residual activity, okay, from 30 minutes until 2 hours and half. So we will see the pattern. How long the enzyme can survive with that kind of incubation. Okay. Okay, any question for this? Before we learn how to interpret the data? Interpret the graph? Any question? You can type if you don't want to talk. Are you there, guys? It's so funny. Am I talking to myself?
No.
I'm talking to myself. Okay. You're good now. Okay. Thank you, Iman. Finally, someone just type something. Okay. So, okay, now we're done with this. We are going to interpret the graph. I'm going to, okay. So, the first thing to do to interpret this, the way we read, we talk about the half-life. Okay, the term here, half-life. Okay. So the half-life here, when we talk, okay, Alian, still, you need to digest this slowly, but We will continue with this, okay? So when we talk about thermostability, we will talk about half-life. Half-life is the um, temperature, not a temperature, the time and the temperature for the enzyme having 50% of the residual activity. Okay, I repeat, half-life is the time and temperature, okay, where the enzyme having 50% of the residual activity. Okay, so now you still remember we we assay each of the beaker, right? We assay each of the beaker just now. Every 30 minutes we have beaker, this beaker. Oops, I lost it. Okay, we assay this and this three beakers, right? So now we know that we have three beakers. Now let's just plot what is left. Okay. What is left? You can see 0 minute, meaning that, okay, 0 minute here is represent the activity of your enzyme when the incubation has not been started yet. Okay, for example, you have three beakers just now, three beakers for beakers for 60 degrees, 65 and 70. So these three beakers, what happened? If we have similar enzyme activity, it will be 100% because we haven't started the incubation. Okay, so that's why it is plot as, oops, that's why it is plot as 100% activity because we haven't started the incubation yet. Okay, so after 30 minutes here, okay, after 30 minutes, we start to plot these three graph, these 3 points, okay, these 3 points. You can see here, 70, wow, okay, after 30 minutes, 70 give you the highest, okay, at 65, okay, at 65 degree, 75%, maybe 70% still there. For this, maybe it is 90% residual activity. I mean, not degree, it is percent. Okay, this one, 75%. Maybe for this one, is only 50%. Okay, so we know that, okay, at 30 degree, this is something that we need to discuss critically. Why? Why it looks like this enzyme prefer to be incubated first at 70 degree before it is, acid and to give you the highest residual activity or something. Yeah, this is something that we can discuss. Okay, so we go for the next reading. Okay, for the next one, we go for the second point, which is this point. Okay, we assay after 1 hour, and then we assay after 1 hour and a half, and then after 2 hours, surprisingly, they are all only having like 25% residual activity. Okay, so the half-life just now, we want to find where is the 50 degree, 50%. Where is the 50% of the residual activity? Okay, so 50% residual activity, it will be somewhere around here because we are talking about 50%. So 50% will be here. Okay. So at least we can just say that if we are using 60°, we still have 50% of the activity after 1 hour of incubation. Okay, but if you use this temperature 70°, the half-life will be here, right? The half-life of 70% will be somewhere here. Oops. Why you don't want to? Yeah. Okay, I don't want this. Yeah, the 50% will be here if you're using this 70°. So it will be, the time here will be almost 80 minutes, right? Yeah. So we get to know at 70°, it will be the half-life for this enzyme for 80 minutes. Okay. Do you understand this? It sounds confusing, but you will get to know because you're trying to find 50% of the residual activity at which temperature. Okay, can you understand this? Just write something, guys. Okay, I will repeat. I will also show you the one I thought I think is easy. Okay, so now we are trying to find what temperature can give you this point, which is 50%. Yeah. So we know that this position, if you're using 70°, this is 70°, this is 70°, this is the plot. So we can have at least at this position is around 80 minutes. 80 minutes, we can get at least 50% of the residual activity if we incubate the enzyme at 70°. Okay, so let's say I have this kind of graph, new graph. I'm going to prepare a new graph. We don't want to have many temperatures. We want to have one. It's okay. It's not compulsory to use 3. So it will be 100% activity here, and then you can see the graph will be plotted like this. Okay, it will reduce. Yeah. So maybe here is 1 hour, 2 hours, 3 hours. So if here is 50, so you know that, okay, around 1 hour plus, you can get the half-life of the enzyme. Okay, so yeah, for example here, if you use here like 60°, if you're using the thermostable enzyme. Okay, if you have another pattern of graph, I'm going to plot another graph here. Okay, we have this graph, and then what if the result shows like this? This is 100%. What if the result shows like this? This one is after 10 minutes. What do you think about this result? Can you use this result, or can you yeah, but your aim is to find the thermostability profile of this. So can you use this result, or do you need to repeat the experiment? If you need to repeat the experiment, what kind of of adjustment should be done. Okay, guys? Do you understand the question? No? Okay, I repeat. If you have this kind of setup, okay, thermostability profile, okay, this is 100% activity because you haven't started the incubation, and then this enzyme was incubated at, for example, 80 degree. After 10 minutes, you assay the residual activity, and then what happened? There's nothing left. I mean, the activity here dropped to 0%. There's nothing left. So can you use this result, or do you need to repeat this experiment with the modification? Yeah, if you need to repeat how to modify. So some people say decrease the incubation temperature. Some people say use lower temperature, okay. Repeat and use lower temperature. Okay, repeat, lower down the temperature. Yes. Yeah. So for this, depending on the enzyme, some enzyme 10 minutes is considered too long for it. Okay. For our enzyme here, for invertase here, we use only 5 minutes of incubation. But for lipase, we use 30 minutes for the reaction time. Okay, if 5 minutes, 10 minutes is considered long enough. Okay, if we 30 minutes, if for lipase assay, standard assay is 30 minutes, but you use only 5 minutes, it will be too short. You don't even know. I mean, yeah, it will not just enough to give something. Okay, so for now, for this case, right, the selection of 80 here is poor. You shouldn't use 80. Use this different temperature. Maybe 55 or 60. Yeah, we need to try because we don't know the answer unless you try and conduct the experiment. Yeah, I know the experiment looks like there's only one graph, something like this or something like this you will get. Yeah, but the effort behind it is a lot. It's not like one time you're done and then that's it. No. Okay, so you need to change the temperature so that later you will get the pattern. Okay. Okay, something like this. Okay, some protein, they are just really stable. Okay, maybe here they are still 60% of the residual activity. So only after 4 hours, then the activity dropped to 20%. So the selection of the temperature also important. So we cannot just I'm scared the enzyme will die immediately. I'm going to choose 25 degree. No, you will, if 25 degree you use and then you know your enzyme at 25 degree can stable up to 4 days, you don't want to keep doing the assay until 4 days, you know. Set up the whole beaker here and then every 1 hour you take for the enzyme activity, residual activity. You don't want until 4 days, right? So you need to be logic. Okay, how do we make ourselves make a logic decision? How do we make sure we make the logic decision? Okay, we need to read from the previous paper. If you're working with, for example, here invertase, okay, so this one invertase, read papers or characteristic about invertase. Okay, if you're working with lipase here and the thermostable lipase, then you will have pattern. Yeah, you will have some characteristic pattern about lipase. You cannot just mix them all, I don't care. No, you cannot do that. That's why literature review is really important when you start your own project. Okay? So that you will, yeah, you can, but forever you will check. You don't know either, okay, I want to use 20, sometimes I want to use 30. Okay, you want to have this pattern. You might think, why do we need to do this thermostability profile? Why? Why it is so important? Yeah, this is important where when you do the reaction, for example, if you have certain application, okay, we are talking about detergent industries. So if we are talking about detergent industry, okay, detergent industries, how do we change this? Okay, so for detergent industries, basically the you know that your laundry stuff, your 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 liquid detergent, for you may think that okay, we just use normal water, normal tap water um, for the washing. Yeah, maybe your tap water temperature is around 25 degree. Your tap water. Okay, basically, if you have put the enzyme, okay, especially thermostable enzyme, lipase, amylase, protease, okay, lipase, amylase, or protease, okay. So this enzyme basically works at higher temperature. We require higher temperature of the enzyme when we talk about detergent industries. Because first, during washing, basically the reaction in the washing machine basically is higher. It's roughly 70 degree and above, even though the tap water is just 25. Okay, I'm not so expert with this, but we can read more about the detergent industries where what basically happen during washing. Okay, same like dishwasher, automatic dishwasher, um, where you wash your dishes, I mean your plates or glass utensil and everything. The dishwasher is basically at high temperature, right? Yeah, so you use um, high temperature, you put some temperature so that it will do the cleaning, really clean. Okay, so when you expose your washing or this washing cleaning, the washing will be completed maybe 30 minutes or maybe, yeah, 30 minutes, sorry, not 30, 30 minutes or maybe 40 minutes or even 60 minutes. We don't know, depending on the type of dishwasher and everything. Okay, for this time, that you need to expose the enzyme for 60 minutes at the heated washing machine or dishwasher. Maybe it is around 80 degree for 60 minutes. You need to find which enzyme can give you the residual activity at least how many percent? At 80 degree for 60 minutes. If it is acceptable to have residual activity around 40% for you is enough, then you need to find an enzyme where the residual activity is still 40% at 80 degree for 60 minutes. Okay, that's why the thermostability profile is important, where you can choose which enzyme can meet my next application, because my application is want to do this formulation. Okay, so yeah, any question for this thermostability before we go for the last part? Hopefully we can finish using this second slot of the WebEx. Are we done? Okay, maybe you want to ask question, you can just write it there. When we go for the final part, which is enzyme inhibition. Okay. Tetra or metal ion, let's see. Or maybe, yeah. Um, okay. So for this one, we want to study for the enzyme inhibition. We want to check which type of inhibitor and then what kind of inhibition that inhibitor gives to the enzyme. Okay, you have learned about non-competitive, competitive, and uncompetitive inhibitor. So we want to know there's no standard saying that okay, PNSF is meant to be non-competitive. There's no like standard saying that okay, assessing of copper will give you uncompetitive inhibition. Okay, so we do not have this kind of standard, but we can see the pattern. We can see the inhibitor style, I mean the inhibitory effect by observing the reaction graph. Okay, so you know from the Michaelis-Menten equation, I believe you have discussed with Prof. Yunus and even with Dr. Sherry last time, where we have the if the Km is higher, okay, but Vmax is the same, that one will be considered as competitive inhibitor. But if we have similar Km but reduced in the Vmax, that one is considered as uncompetitive inhibition. Okay, but if we have reduced both, no, we have reduced the Vmax and increased the Km, there must be some non-competitive, right? So we have, yeah, but we need to check. I'm not sure with that one. Let me check again here. Non-competitive, okay. Competitive inhibition. It's better to check. Okay, have only this. Yeah, maybe line vertebrate will be easier for you. Then we can see clearly. And then also this one, the Michaelis-Menten. Oh, this one looks easier. Okay, this one also looks easier. Okay, this one line vertebrate for 3 inhibitors. So we have here, can you see the picture here? What's the graph? Okay, this one. I'm hoping for something more beautiful than this. Okay, this one. Yeah, this one. Okay, so we can see here, if there is no inhibitor, there will be like the highest product formation here. Remember, we have substrate concentration versus rate of reaction. Then we have the Vmax. We have done this experiment effect of substrate concentration in your practical. Okay, so here without the inhibitor, you can see the Vmax here, and then the Km is just here. This is the position of the Km, and then once we have included the competitive competitive inhibitor, where your active site will be the active site of the enzyme. Both of the inhibitor and the substrate will compete for the same spot. So for this case, we can see that to get the similar Vmax, you need to have what happened? Okay, to have the similar Vmax, here, you need to increase the Km. So Km now from this number has increased to bigger number because the presence of the competitive inhibitor. Okay, so for the non-competitive inhibitor, okay, so what happened now for non-competitive inhibitor, where the inhibitor bind to the allosteric site, it will inhibit, it will change the structure of the active site. So what happened? The Km will be the same, but the Vmax will be reduced. Now from this Vmax is just reduced to the lower Vmax. Okay, so now if you look at the Lang-Weber equation, you can see here, this is without the inhibitor. Okay, but once we have added the inhibitor, the Km from here has shifted to this. So in this case, the Km just increase. Okay, so yeah, it is just inverted version for the S here, because we have used 1 over S. Okay, but the Vmax are still the same. So this Vmax basically similar to this Vmax. So if you want to get to know what kind of inhibitory effect of the experiment, we need to have this kind of graph. Either you want to do Lang-Weber or Michaelis-Menten. Okay, so if we have this kind of, okay, 5 minutes or 30. Okay, I will make it really quick. Okay, so if we have this, why? Okay, so if we have this, okay, we can see the difference between each of them. Okay, competitive inhibitor, the one that we have discussed just now, uncompetitive inhibitor, uncompetitive, we can see the Km reduced, the Vmax also reduced. For non-competitive, where the allosteric site being placed, being attached with the inhibitor, then Km will not be changed, but the Vmax will be reduced. Okay, so the Vmax now has been reduced. Okay, so to do the experiment and everything, you need to have this setup. You need to prepare all of this reaction and then put the inhibitor. So for now, for table 6 is the one without inhibitor. You have put substrate, okay, increase into the substrate, because remember, you need the substrate here. You need the x-axis as the substrate. So that's why you put different concentration of the substrate. Okay, so now you're going to put the second set, that means for the table 7, similar substrate. Okay, and then you can see when you add the copper sulfate here. Copper sulfate here is for the inhibitor. Okay, you can see at which concentration because after the experiment you need to plot the graph. What happened here when I'm in hurry? Okay, so you repeat similar set of the experiment when you use aniline. So you have copper sulfate and aniline. Even Michaelis Menten graph still okay, so that you can see how does the graph looks like, so that you get the answer. Which one is competitive, which one is uncompetitive, which one is non-competitive. So you can also try to answer this question so that you get to know more about the enzyme. Okay, I think that's all. We can start the new session if you have any more questions. Okay, we end of this second set, and then we're done with the characterization of the enzyme. So maybe you can set another one more link so that we can have a short Q&A session if you have. So see you in a minute. We're going to finish. We're going to end a few seconds more, right? Yeah, just get ready with your question, then we can type in that. Okay. Are you okay so far, guys?